Good morning, good afternoon, and good evening. Welcome to the latest installment of our series, which is part of the Hamlyn Symposium, which comes to a culmination at the end of the month with the final closing ceremony next week. And today I'm absolutely delighted to introduce a colleague, a friend, an entrepreneur from UCL, and his name is Dan Stoyanov, which many of you in the audience will know. So Dan is Professor of Robot Vision in the Department of Computer Science at UCL, where he's also the director of the Wellcome EPSRC Center for Interventional Surgical Sciences, also known as WACE. To top this off, he's also the Royal Academy of Engineering Chair in Emerging Technologies and Fellow of the Institution of Engineering and Technology. Dan first studied computer science and electronics at King's College London, which is also where I did my undergraduate, before completing a PhD with us in the Department of Computer Science at Imperial College, where he specialized in medical image computing. He works on vision problems in minimally invasive surgery, especially related to non-rigid structure for motion, scene flow, and photometric and geometric camera calibration. His work is applied towards developing image guidance, computational biophotonics, imaging modalities, and quantitative measurements during robotic-assisted minimally invasive procedures. As if this was not enough, Dan is also Chief Scientific Officer at Digital Surgery, which was recently acquired by Medtronic for an undisclosed but a healthy sum, and a co-founder of Odin Medical, both of which specialize on developing AI products for interventional healthcare. I'm thrilled to introduce his talk today, which is entitled Towards Understanding Surgical Scene Using Computer Vision, which will be followed by our usual Q&A. Dan, if you'd like to share your screen, I very much look forward to your talk. Thank you. Wonderful. But you're muted.
I'm just trying to unmute myself. So it doesn't seem like I can start my video, but I've been able to unmute myself. So thank you very much.
Can you see? Can you see now me asking you to start your video?
Yeah,
that's it. Wonderful.
All started now. Fantastic. So thank you very much for this introduction, Ferdy. It's a real pleasure to be speaking at the Hamlyn Symposium. It would have been wonderful to do it in person, and I very much hope that we can do so next year and in years to come. But in the meantime, it's really a pleasure to be able to host this seminar and to speak about some of the work that we've been doing on computer vision in surgery with a view of how we understand surgical scenes. As most of us know, digital cameras are present in most modern operating rooms, and they really are a means to facilitating surgery either through keyhole ports, so minimal access, or through natural orifices, or by magnifying surgical sites or allowing non-invasive diagnostic imaging capabilities. So there's a plethora of digital cameras, from endoscopes to microscopes to pills that capture visual information. And as humans, visual information is one of the primary senses that drives our decision making. And of course, that's also the case in surgery. So the visual field of view is an extremely important sensory mechanism in order to decide what activities to perform, which parts of the anatomy to manipulate, and so on and so on. And of course, with the rise of artificial intelligence, and in particular computer vision, we now have a means to take information captured from the surgical site and potentially use it in order to perform automated analysis and to understand a variety of important questions that are important for real-time assistance, but also for post-operative analytics. So these are just some examples of the type of anatomy that might be observed by a range of cameras during surgery. And as one can see, there's quite a lot of variability, and that's due to the shape and the photometric appearance of the anatomy and of the organs, but also a variety of instruments, magnification types, and so on. So the type of data that we're capturing is quite diverse. And it's also enormous. So surgical procedures can take anything from 15 minutes in cataract surgery all the way through to many, many hours in some more complex procedures. Recording and capturing this visual domain over such a long period of time with increasingly high resolution generates a tremendous amount of data. And today, for the most part, this data is either not utilized at all and not stored, or it's utilized predominantly for R&D. But I think we're now at the cusp of when this data is actually going to start being captured and creating and used to create clinically meaningful solutions. So the visual domain can really be divided into a number of axes. So when we talk about surgical scene understanding, we could mean semantic understanding, so understanding the presence of different anatomies, of different instrumentation. We could mean spatial understanding, so the 3D geometry and kind of mapping of where you are within the anatomy, or a number of other dimensions of the domain, which could be around activity recognition or the spectral aspects of it, and so on and so on. And today, I really want to focus on the spatial component of surgical scene understanding and talk about our ability to understand the 3D shape of surgical sites. The reason why this is important is it's a precursor, so the capability to understand 3D shape and to map the 3D structure of scenes is really a precursor to enabling enhanced navigation and potentially augmented reality, to providing analytics and analyzing the 3D space of activity, and potentially to enabling new imaging modalities, because for certain physical imaging modalities, we may need to know the angles and the shape of the surface of the tissue with respect to the illumination sources and the imaging sensor. Spatial understanding of the surgical scene is also critical for enabling robotics and automation. So doing any sort of autonomous robot control or assistive control, or potentially for enhancing instrument capabilities. So creating smart instruments that might respond to where the instrument is with respect to the anatomy and so forth. So really it's a key feature of any advanced, more intelligent medical robotics or surgical robotics platform to be able to understand 3D space and shape. And we've been working in this area for a number of years, not just ourselves, but the community, of course. And here you see some examples over the last 10 years of how you can take stereoscopic images from Da Vinci or other systems that use stereoscopes and generate 3D depth information, 3D flow field information, so motion fields, how you can use this information in order to calculate the motion of the camera, which is obviously important if you want to maintain the alignment of navigation systems, and potentially map out very large scenes, understanding the full shape of the surgical site. So all of the examples that I'm showing on this slide here are using model-based vision. So we model the problem, we model the similarity metrics that we're trying to compute, and then we take images and essentially execute these algorithms over them in order to infer 3D information, camera motion, and so forth. And of course, vision over the last 10 years has changed dramatically from model-driven vision towards data-driven vision. And deep learning has really allowed vision to become so much more robust than what we were able to do previously. And we've also adopted this trend. So this is some work published a couple of years ago where we start using deep learning to perform computational stereo on the surgical images. And the key advantage really is that suddenly from a model-based approach where, for example, you need to specify a specific disparity range, so you're limiting the size of the surgical site, you can suddenly actually expand this to be much larger without having a dramatic expansion of the computational cost. So once this model is trained, you can load it in GPU memory and you have very, very fast inference times. So you can essentially do real-time 3D depth estimation very, very effectively. In addition to improving the computational efficiency, you can also potentially improve the performance of the stereo algorithms by using different architectures in order to ensure that you're capturing a wide range of sizes in your correlation functions, so that you can essentially calculate very, very fine detail as well as higher level features in regions where there isn't so much textural information in the image. So these systems have become extremely effective at calculating 3D depth. Something that we've been looking at more recently, and this is not published yet, but we're hoping it will be soon, is how do we start not only doing 3D estimation on its own, but actually start combining some of the tasks that you might want to run over an image. And in this case, we're particularly interested in how do we achieve instrument segmentation, so segmenting the parts of the image that are instruments versus the parts of the image that are tissue, and do this jointly with the disparity estimation. And the reason why this seems a sensible approach is that usually instruments occupy parts of the scene that are much closer to the camera. Therefore, they create quite strong discontinuities at the instrument boundaries. And if we use classical regularization techniques, essentially this discontinuity isn't preserved, and you end up with smoothing artifacts. So potentially by training networks to solve the problem in a multitask fashion, we may be able to get disparities that preserve edges and preserve discontinuities, and at the same time improve the tool segmentation, because we kind of have an obvious prior that instruments should be above the tissue rather than inside it. Of course, that can be violated when the instruments are when they're interacting with the tissue. So one thing to spot is that if you run these architectures separately, so if the top is an architecture for instrument segmentation and the bottom is an architecture for disparity estimation, you actually notice that the feature extraction layers are very, very similar. So if you do these in series, you're essentially not being particularly computationally efficient. So there's also an opportunity to actually improve the computational abilities of these models by combining them. So if we try to do this in a multitask fashion, essentially we combine the feature extractors. So we try to use the same feature extractor to solve both the segmentation problem and the disparity estimation problem. And this can essentially lead to better performance, because rather than running things in series and extracting features for the segmentation head and then going forward and extracting features for the disparity head, we can potentially try to parallelize this and make it more optimal. So in our proposed or what we're developing now system, we're essentially using the same feature extractor in order to try to optimize the runtime performance of a multitask system that at the end is able to generate both the instrument segmentations and the disparity map at the same time. And this can potentially scale linearly. So if we can crack this problem, or solving problems like this in this type of fashion, the number of tasks that you add would lead to linear scaling of your computational costs. So if in addition to segmentation we decide to add another task, this wouldn't necessarily explode the computational cost of the approach. So this is why we're interested in developing techniques like this. So if we look at experiments that we're running at the moment, if we look at how approaches like this may perform, we also notice that in fact, approaching the problem in a multitask fashion, so training the feature extractors to solve multiple problems, may also result in positive learning. So result in models that can actually perform better than when they're trained and optimized individually on just the segmentation or just on the disparity. So here we see the type of accuracy you may get for segmentation. So these are this is a segmentation only, and then when we train segmentation and this is disparity only, we can see that you end up with lower disparity costs. And then when we train everything jointly, we actually end up with lower errors for both parts of the problem. So in essence, the network is learning how to positively learn from each of the problems that we are training it to solve. So this is very new work for us, and it's showing some quite encouraging features that we can start training multitask learning networks. Now, of course, one of the problems is that the amount of data that is available to train models like this is extremely low in surgical computer vision domain. So this is some examples from the SCARED dataset, which was released by Intuitive as part of the EndoVis challenge in MICI 2019. And here we're just demonstrating what multitask learning may be able to do. So at the top, you see a baseline model. So this is essentially a disparity estimator trained, pre-trained on the scene flow dataset, which is a synthetic dataset, and then applied to these surgical images of porcine anatomy. So you can see the model that's trained on synthetic data generates quite a lot of errors in particular regions, either when they're highlights or when things are really dark and far away, and so on. So we can notice that the pre-trained model doesn't work very robustly. That's not something particularly unusual. It's quite normal to fine-tune models. So we can see that if we train a supervised model like this on the SCARED dataset itself, we can have much better performance with respect to these types of artifacts. Now, what's interesting is that actually, if we fully supervise the segmentation head of our multitask model on segmentation data, but we don't include any of the disparity data, we can also get a similar improvement in the performance. So here we're not using the disparity, so we're not using the SCARED dataset in order to improve the model. It's using the segmentation in order to improve it. So there's a transfer of information between the different types of dataset that you might be training each of these independent tasks. So I think this is quite exciting, and I think this is an area that will be. This is another example. So again, you see scene flow pre-trained on the scene. You see a model pre-trained on the scene flow dataset and how it runs on the surgical data. You can see that there's a lot of errors, particularly due to the intensity of the images. We then see that you get a model that is able to estimate the depth more robustly and also segment where instruments are. So this is a multitask learned model. And then you see that you have a fine-tuned model, which is essentially trying to continue to optimize the segmentation information. So continue to optimize the multi-tune model on segmentation, and is able to get the results to be even better. So the multitask model essentially means that we can now train quite good instrument segmenters and jointly get the disparity information. So really promising results, but quite early days. And we've evaluated this approach on the SCARE dataset, which was released by Intuitive, and we can see that actually without doing any depth supervision on the SCARE data, so no supervised learning in terms of the depth estimator, we're able to get near state-of-the-art performance without any training. So I think this is an exciting area as we try to transition vision systems to be less and less supervised. Now, I should say that the SCARE dataset, although it's really, really exciting, doesn't come without its problems. And we can see that some of those problems are with the rectification of the images, where the calibration goes offline. And these are kind of common problems that we encounter in computer vision for surgical systems that sometimes are considered to be solved, but in practice, they really aren't. So even in a controlled lab environment, when you move the camera that's mounted on the robot, you know, things don't tend to move very nicely, and this induces errors even in quite controlled circumstances. So I think there's quite a lot more work to do in terms of developing new, really nicely aligned data sets. So I'll just show one of the data sets that we've released recently, and it takes a very different approach to the SCARE dataset. So the SCARE dataset generates ground truth using a spectral approach, structured light. In this case, we're taking a more classical approach where we're using tomographic scanning in order to get CT data. So this is, I guess, this is closer to what would happen in a clinical system, because the patient would get the 3D anatomy generated from tomographic imaging, and we try to align this information to the video images that we acquire of the cadaver anatomy, and then we manually try to refine this alignment. And you might ask, why do we manually try to align it when you can insert fiducials and so on? I think the answer is that it's really tricky to get the fiducial systems to work. That's because the scanner moves, the robotic arm may move, the endoscope goes out of line. So all of these, they can be very small vibrations. They tend to introduce error, and controlling that error is very difficult. I do hope that we can get to the point where we're going to crack this, but we haven't managed this today. So manual alignment was still very important. So in the end, we have generated a data set which, with the manual alignment, we're able to then generate the depth maps from the CT scan, generate disparity maps, occlusion maps for where things are not visible in both images, and generate rectified stereo frames. So all of this data is now available, so hopefully it supports some validation of what is possible. I wouldn't say that it's better than the SCARE data, it's just different. It comes with its own challenges, just like the SCARE data comes with its own challenges. The SCARE data is better resolution and looks higher fidelity because it wasn't in cadaver, and also the scope is a higher resolution. Both data sets are useful, both have their own problems, would be my take on it. In essence, we've got 16 stereo samples from 2 different torso cadavers, 2 different scopes, so 0 and 30 degree, and we provide the dense disparities, dense depths, and also the occlusion maps. And I'll just show a nice rendition of what the final data sets look like. So these are available for download and for use today, and they're getting some interest. So I've spoken about what is our current work in terms of estimating 3D shape from stereo, but of course, a lot of surgery is not performed using stereo systems. And both ourselves and others have been looking at how we try to estimate 3D without stereoscopes, either in monocular laparoscopy or in endoscopy. And one approach is really to use synthetic data and to try to do domain adaptation to real data using GANs or conditional GANs. And this seems to be proving to be quite effective. So I'll just show some of our recent work in this space where we're taking synthetic data, top right. So this is data generated in Unity. And we're able to train monocular depth estimation networks. Some of this work actually originated at UCL originally, but it was used for autonomous vehicles, and we've adapted some of these models to endoscopy. In essence, you can train on this synthetic data, and you can make the model work on real data. It's not bulletproof, but it seems to perform quite well. And we now have a really exciting focus project called EndoMapper, where we're in a European consortium led by the University of Zaragoza, where we're developing vision systems to advance what is possible in an endoscopic vision like this. Of course, estimating depth is just the beginning. Ideally, what you want is to be able to estimate depth at each point where the camera traverses a particular anatomy, and then estimate all of the camera poses and really reconstruct the full geometry of that anatomy. So take for example, in colonoscopy, take a colonoscopic video and then generate a full 3D reconstruction with all of the camera poses and generate the full 3D colon model in order to understand what has been observed and what hasn't. And I think we're making some advances towards achieving this. So this is some very recent work from Anita, who's part of my group. So here we're using our synthetic data to train the depth estimator. We're also generating the camera poses as the camera travels within this Unity environment. So we can then take the camera poses and look at how we train not just the depth prediction, but also go for generating the pose prediction at the same time. So this is quite recent, and we're just in the process of wrapping it up and submitting it. So this is essentially learning how to estimate pose without explicit feature detection. So this is real data mutual correlation. You're training a ResNet model, so you're taking the video and taking 4D correlation models and trying to do the matching or the kind of the pose estimation using this highest correlation matching technique, which then should yield 60 camera poses. So these are a couple of trajectories where we can see the ground truth is in blue and the single image prediction is in red. So the relative prediction is actually pretty good. Now, when you run this as a cumulative prediction, it tends to drift out, but you can see that the shape of the trajectory seems to be following a good pattern, and we're just in the process of trying to optimize this in order to alleviate this drift. So a similar problem, but in a very different application, is estimating the pose of the camera during photoscopy. So in photoscopy, the objective of the procedure is really to photocoagulate all of the vessels on the placental wall in order to sever blood flow between two twins. And the purpose of estimating camera pose here is to generate mosaics in order to visualize a wide angle view of the placenta and be able to be sure that all vessels have been photocoagulated. So we've been taking a deep learning chromography estimation approach to this problem as well. So this is some work that one of my colleagues in 2019. Recently, last year, we advanced it to perform more stably and generate better fidelity mosaics by looking at the vessels, so segmenting vessels from the images, using those vessels in order to perform the registration between consecutive images, and then doing the pose estimation on these vessel-nessy images. And this seems to work really, really well. So it seems to generate much better mosaics than doing things directly on the photoscopic image. So this was presented at MICI last year, and most recently we now do a final optimization step. So this is work that's going to appear very soon in Robotics and Automation Letters. So again, we're taking these vessel-ness images and we're doing a final post-graph optimization in order to optimize the results over the entire sequence. And this leads to mosaics that are actually just have a lot less artifacts. So you can see in the top image here, you can see how the vessels are aligned much better. And also, this technique can be used to also with non-vessel-based images, so with more traditional feature extractors in normal laparoscopic images, in order to generate nice field of view expansions in laparoscopy as well. So this is just the final optimizer at the end of the mosaicing pipeline. So I started by saying that I'll only talk about the spatial aspects of the domain of information that we might infer from images. And of course, there are lots of other really exciting axes of this domain. It could be the temporal axes, so recognizing activity and events and phases, and there's a very active community working in that space. There's also the spectral, looking at how tissue and light or other energies interact with each other. And of course, the more robotics orientated aspect. And so I'm very pleased to point to these recent review papers, which I'd encourage people to read if they want to get more of a global view of what is possible with vision and with surgical scene understanding. The latest one of these around the DVRK, so reviewing 10 years of research with the DVRK, will resonate with the symposium very, very well. I've already seen Peter Kazantzidis from Johns Hopkins speaking about the DVRK. It's been a fantastic initiative, fantastic to be part of it, and really exciting to see this 10 years of research that has been achieved by using such a platform. So I hope this has been a nice perspective on some of the things that are possible using computer vision. And I'd like to thank you for this opportunity and thank my group and funders, and in particular for this presentation, Dimitris, Sophia, Liang, Anita, and Eddie, who did all of the work and the actual research that I've presented today. So thank you very much, and I look forward to the Q&A session.
Wonderful. Thank you very much, Dan. And I see some familiar faces, Eddie, but Sophia actually did her MSc thesis with us in MIM. So talk about a small world. Fantastic presentation. As usual, I'd like to thank our speaker for taking the time to present to us, and encourage the audience to ask questions. The way we do it is via the Q&A tab. And I see there are a few questions here already that I'll be posing to Dan. As you think of your questions, please feel free to type them in the tab so that I can put them to Dan as soon as we get to the particular one. So the first one we have got here is from, I think this one came first, and it's from Beirut. In the multitask approach, 3D and segmentation, how would you evaluate disparate estimation performance, and do you have ground truth?
Right, yeah, so we've been evaluating using the two data sets that I mentioned. So one of this is the SCARED data set, which was released by Intuitive. I think the paper is now live on arXiv, and the data is available for download. So that contains quite a few sequences, and it does have ground truth. It's got some problems occasionally with it, but it's one of the best data sets out there. And we've also been evaluating using the data set that I presented, the SURF-CT data set, which is generated from tomographic data. So those are the two data sets that we use for evaluation. They're not without problems, but it is the best that is available today. I'm really excited I'm hoping that over the next year, we'll be generating more and more data in this space, and hopefully getting it to be more and more refined. So that's how we've been doing the evaluation so far.
Then drifting away from the questions here, I'm going to get back to very quickly. But since we raised the topic of data, you have been particularly enlightened with the work you've done with touch surgery and so on, bridging that gap between the sort of openness you'd expect in academia and the sort of need to protect that as a form of IP in industry. So I do wonder whether through that particular experience, which is quite unique to you in this domain, you have some pearls of wisdom as to how we could encourage more of our fellow researchers within the industrial community to be more forthcoming with some of that data, because of course, as we move towards machine learning, the access to data, I mean, data as a new oil has come up as a recurring theme throughout this keynote series. And so clearly getting everybody paddling in the same direction is a great plus.
I mean, I wish I had a succinct answer. I don't. I think my take on it is that the more that our community transitions into the industrial research community, the more appetite there will be for people to collaborate and to open some of these systems. I think that's essentially what's happened with some of the big IT companies or the tech giants. They've got really, really vibrant research labs, and those researchers are quite open to collaborating and, where appropriate, releasing some bits. It's not always that way. I think we're seeing the same. The SCARE dataset is generated by Intuitive and released by Intuitive. The DVRK, the same. We released the dataset around cataract surgery segmentation last year from Digital Surgery and from Medtronic. So I think there are signs that people are beginning to open up. Obviously, it won't be you won't release everything that's commercially sensitive, but certain data sets, particularly when you're running it with a challenge together, so you're stimulating the community to kind of contribute to it, I think there is going to be appetite and collaboration and openness from industry there.
Lead by example, and I think as long as we demonstrate that with those examples where industry has shared, actually has come back to them with a percentage increment, I think that will be the easiest way to convince that actually there is method to the madness. I see that Doro had a follow-on question with regards to his original query, and he says, is the multitask approach to 3D and segmentation model trained supervised? Which I'm not sure I'm putting the emphasis on the right part of the question. Is the multitask approach to 3D and segmentation model trained supervised? There's a lot of verbs in there. Maybe you get it.
Yeah, no, it's a good question. So obviously you can do full supervision. I think the one thing that we're seeing that's quite interesting is that actually you can pre-train on non-surgical data for the depth estimation. Then you can train the multitask model just embedding the segmentation from the instruments, so not the 3D information, and the model tunes. And so there's an exchange of information between the labels that you might get as segmentation and the depth information. And so I think this needs to be explored further. I mean, there isn't really sufficient data at the moment to be able to kind of really understand the behavior and how this data transfers between the different data sets. But the indication is, and what we were excited to see, was that actually you can avoid supervision on the disparity. So you can avoid the 3D supervision and still get decent results. So I think that was an exciting finding that we're hoping to present.
Wonderful. Thank you, Dan. I'm going to have to sort of move on to others, even though there is a follow-on to a follow-on. But I think in the interest of time, we've got the next question from Nabil, who asks, what do you think are the biggest challenges of the rising technology within the healthcare surgical procedures, healthcare system surgical procedures? So what do you think are the biggest challenges, I guess, within the rise in technology within the healthcare system and surgical procedures? Biggest challenges. So the biggest challenges within our broad context of CAS or RAS.
Oh, it's a nice, easy question, right?
Beef, yes.
I mean, well, the most obvious at the moment is COVID, but if we avoid that one, I think for the kind of the topics that I've discussed today, so the more AI aspect of things, the challenge is really managing data, creating the infrastructure, and then once you've got the infrastructure and you've got the data and you can build these AI models that solve a particularly interesting problem, is then how do you deliver that technology back into the theater and really understand the human factors of where it adds value, where it adds complexity, sort of work through that. And I think it's the similar experience of, I think the initial findings of using a robotic surgery system were that it increased the time of the procedure because everyone was getting used to using something new. And now it's kind of optimized and procedures are getting better. But I suspect that with any new technology entering the space, there's going to be a similar
100%.
A similar learning curve. So yeah, I think from a practical point of view, getting the infrastructure there, getting the data collection, getting the legal agreements, or understanding how data is able to live in different geographies and how your models are able to be deployed in different places. This is a challenge to the academic community because we're usually not very well versed in it.
Yeah, absolutely. Indeed. We also have a question from Lalith, and he asks, did you face problems with endoscopic artifacts like occlusion and fogging? And were they perhaps dealt with in a special way?
Yes, those are problems. We haven't done anything to do with fogging or with smoke at the moment, not in the models that I presented. We have historically, we've worked on desmoking and we've got some papers. There's some other really nice papers published by other groups as well. In this particular case, we didn't. One of the reasons is that the SCARED and the SERP-CT data sets don't contain any of that data. There's an earlier data set that was published in TMI, led by Lena Meyer-Heim in Heidelberg, that does contain smoke, but there's other problems with that data that make it difficult to use. So I think it's an important problem. I think I've seen some work recently, perhaps it will be appearing at MICI or at CVPR and so on, around approaches that address the kind of the illumination conditions and also the smoking as well.
Brian asks, you showed that the mosaicing task was significantly improved by including the segmentation maps of various vessels. Do you suppose that tasks such as this will be further improved when using multispectral data or optics?
Ooh, hopefully. I guess multispectral data, depending on the kind of the resolution and various other things, may give additional information. Hopefully, information below the surface, which would be useful. I think the challenges there are obviously capturing that data in a way that can be used for processing. I think there's still some limitations in terms of how that data can be obtained. But hopefully, yes. And I think one of the exciting things of taking a data-driven approach rather than a modeling approach, the way that we used to years ago, is that potentially if the data is getting better, the solution should be getting better, and you should be able, without you fine-tuning and tinkering everything. So I think that should be an exciting way that things go. I'm not sure if it will be, but hypothetically, that's how it should be.
Dan, let me just sort of shoot off on a slight tangent here. So you've been doing this for years, and actually your PhD was on this already, right? So in a sense, data-driven approaches offer this incredible increase in what you can hope to do. Are there any pitfalls from where you sit, having tried them both ways and having now an entire group that is moving in the direction the whole field is moving, which is sort of data-driven? Are there any things that researchers should be keeping an eye out for? Any pitfalls, any cons, or is it just pros? Yeah, because
I mean, the challenges are, if you go for supervised learning, the challenges are getting the right data. There's no beautiful 3D data to do supervised learning. The other challenges are how do you do domain adaptation, so that if you're suddenly in a different part of the anatomy, how do you make sure that your system is going to work? But I think those are interesting challenges to work on. So I know that this year at MICI, there is a domain adaptation challenge purely on the domain adaptation problem, which I think is really, really exciting. So I think with data-driven methods, that would be one of the big things that we still need to tackle. And if it can be tackled, then of course it opens up this whole unsupervised area. So can we train on simulators? Everything is in simulation, but actually we train these models that can apply to real cases. And then how do we make sure that there isn't bias? So if there's things that are observed very rarely, can your models still detect them? Or that sort of stuff, I think is really where we need to innovate and advance the state of the art.
And I honestly think on the imaging side, the pros by far outweigh any possible cons or shortcomings of this. We now have an anonymous attendee who asked the following question. Thanks, Dan. My question is about multitask learning. Did you learning the model separately in each task or learn at the same time? Which one would you recommend?
Sorry,
yeah,
I missed,
so I'm gonna try to
I missed the question.
Did
you mean
you
whether
learn
you
the
learn
model
it?
separately? So this is in the multitask. You learn, I guess, so your two learning processes were in series or in parallel. I think that's paraphrasing what you're asking.
Right. Yeah. So it took us a really long time to get it working in parallel. That's all I can say. But it does seem promising. So now we're going towards the parallel direction. But in the initial phases, and this wasn't intuitive, the separately trained systems perform better. My suspicion is that that's a data problem. The data sets are still not sufficiently large for us to be able to say that this is the methodology versus actually this is just like such a small sample of data that you're not really, it's not really learning in a consistent way. So I think we're now going towards parallel, and I think that's the exciting direction to go.
Following on from this, the question continues with, is there any benefit with cross-modality image in the medical application? Is there any benefit with cross-modality?
I would say yes, but I don't know exactly what the question is asking. So multimodal always sounds good to me.
It's a little bit cryptic, but we'll say yes, leave it there. But if the anonymous attendee would like to clarify, we can try to post that question as well. Stephanie, I see, has only written hi Dan, so I guess it's hi Dan from Stephanie. And in the meantime, Gabor Schichtinger, he asks something. Hello, Gabor. He asks, open surgery is still the most frequent use of surgery. I wonder how laparoscopic vision techniques translate to extracorporeal vision. Do you have some insight into the crystal ball of extreme domain adaptation?
I mean, I wish I had a crystal ball. I think we have been working on a wearable camera actually, and kind of taking the same approaches from laparoscopy, for example, for phase estimation or detection, using a wearable camera in open surgery, and the results are actually quite promising. And I think it is a space. The domain is more challenging because it just those cameras move around even more, and it's just really difficult. But I think there is promise. There's other challenges as well. So anonymization becomes much more difficult because you're not just looking at internal anatomy, you're looking at the whole scrub team and anyone else that goes into the OR, students and so on. So that's a particular challenge. The dynamics of the video are very difficult. So I think it will be much more difficult to do things like develop navigation systems based on that data. But for things like analytics and potentially event detection and so on, I think it could be quite useful. There's also some really nice work coming out from both companies and academia around using cameras that are mounted in different places in the OR, estimating where people are, estimating activity and so on. So I think it is coming. It's a harder problem because the domain is more dynamic.
George Milonas is dabbling in this area as well. I think he's got some good ideas. Let's see what comes out of that. In the interest of time, we got Stephanie, who did put a question in. I think we'll use it as the last parting question for Dan. And she asks, do you think we need additional metrics that take into account clinical impact, not only classical deep learning metrics, example, regarding semantic segmentation?
Absolutely, yes. But I don't know what they are. But it's a bit, I do like annoying my students when I say, there's 2 pixels more or 2 pixels better. Does that mean it's actually got any clinically meaningful impact? And I mean, I don't have the answer, but it would be very nice to know what it is that we're chasing. So is it that we need to really kind of refine and optimize on these data sets and get these fractional incremental changes? Or are there more important other challenges that can make these systems work in practice and actually make them into clinically useful systems?
Indeed. And talking about specular reflection, look at that. Yeah, that's the sweat on the forehead because it's like 45 degrees in this office because in the spirit of being ecological, we got air conditioning for the researchers, but the academics in cellular offices, we got mechanical cooling, which basically means you open the window and you hope deeply that by opening door and window you get some current, but clearly not today, especially because I keep the door closed. So with that, I'd like to thank you again for taking time to present to us. It's been absolutely enlightening. Remind everybody that if you have missed this keynote live, it will be available on the YouTube channel for the Hamlyn Symposium in the next couple of days. And remind you there are a few more lectures, including one from Elena De Momi for Polytechnico di Milano later this week. And then, of course, our closing ceremony at the end of next week. So without further ado, thank you to the audience. Thank you, Dan, and I will see you soon.
Thank you.
Take care.
Bye-bye.
Bye-bye, everyone.